Wrong slide. Okay. All right. So if you remember, 2 weeks ago, before the spring break, we were talking about leader election. We're still in this chapter that describes all these canonical problems in distributed systems. We've covered a fair number by now. Okay, we are towards the end of that chapter. We did clock synchronization, we did leader election, we did distributed locking. Okay, so we cover, and then we looked at distributed snapshots, termination detection. So we've done a whole slew of these uh, problems that are canonical problems that you encounter in any distributed system. Okay. Today we are going to continue from that point on and look at the very last topic or subtopic within that chapter, which is transactions. Okay. Now this overlaps some with a course in database systems. So if you've taken a grad level course in database systems, some of what I may be talking about today may sound as a repetition. Even if you've taken an undergrad class in database systems rather, you may have encountered some but not all of this concept. Okay, what we are really looking at here are not transactions themselves but distributed transactions and how you can use distributed databases and things like that. Okay, but I'm going to start with this notion of a transaction, define what it means. Okay, after I covered some basics, we look at distributed transactions and then start thinking about how you can implement distributed transactions. What kind of techniques might you employ to implement such a mechanism? Okay, so I presume all of you have heard of this term called transactions. Okay, let me define what that means. Transactions are a mechanism for providing atomicity. Atomicity is basically an all or nothing property. So if you say that a certain set of operations are atomic, that means they all operate or they all execute or none of them execute. Whenever you have anything encapsulated, any operations encapsulated in a transaction, you will never have a situation where some of those operations complete but others don't. So they all execute as if they are one logical atomic unit. Okay? That is what a transaction mechanism will give us. I'm going to show you examples of why you need them and so on. Okay? So clearly they have their origins in databases. You must have heard of databases and transactions and whatnot. Okay? So here is a banking example that even tries to motivate why you need this concept at all. Why do you need a sequence of instructions or operations to execute as if they are one logical unit? Okay, so let's take a simple database. This is not even a distributed, simple centralized database. Let's assume that there are two client applications that are making updates to the database. Okay, and so this is basically column 1 shows the operations that client 1 is executing and client 2 is executing these instructions or operations. Okay, time is actually on the vertical axis going down. So all that is actually happening in this case. Okay? Client 1 is taking some money from essentially account A and transferring it to account B. Okay, so essentially client 1 is transferring $4 from A to B, and client 2 is transferring $3 from account C to account B. Okay, so essentially both of these clients are moving money from two different accounts A and C into B. Okay, it's a very straightforward example. And here is how this is not even a transaction, but here is how the instructions are going to execute. So essentially client 1 is going to read the balance of A, okay, which is 100. It's going to deduct $4 from that and write 96 to the database. Okay, and then is going to take the balance of B and presumably add $4. Okay, and client 2 is going to do the same thing. It's going to take the balance of C, deduct $3 and take those $3 and add it to the balance of B. Okay, so far so good. So here is what happens when they are executing in parallel. Because the assumption is both of these clients are executing concurrently. They're making concurrent operations on the database. Okay? And what is shown on the y-axis here is the exact sequence in which these statements are going to be interleaved. Okay, how they're actually going to execute. So client 1 is going to read A, deduct B $4 and write 96, and that's fine. And then client 2 is going to run. Okay, let's assume that this is just two applications that are time shared. Okay, so we may switch from context switch from one to another. Okay, so let's assume time slot or quantum for A is done and B runs. So B is going to read 3 and C's balance, or rather 2 is going to read C's balance, deduct $3, let's say, times slice ends again. Then you switch back to client 1, you read the balance of B. Okay, you switch back to client 2, you read the balance of B. Okay, both of them have actually read it at the same time at this point. And then 2 is just going to add some money to B and write it out. And then when you switch back to 1, it has actually read the balance before 2 ran. So it's going to simply add $4 to the old balance. And what you've ended up at this point is you deducted the right amounts from these two accounts. But what B is left with is 204, not 207, as you would have expected it to. Because you basically overwrite one client, overwrite some other client's work. Okay? So you're left with an inconsistent state. So this leaves, if you had this in a database, your database would be in an inconsistent state. Because you do not expect this to happen. You would have expected the end balance to be 204. Okay? And that would have happened if each of these clients ran sequentially. Okay? If you took a global lock on the database, okay, clearly database is a shared resource here. Okay? So if you implemented a global lock, then client 1 might have grabbed the lock, it would run to completion, and then client 2 would grab the lock and run to completion. Okay? The simplest approach is to treat a database or any data structure as a shared object, implement a lock. Okay? But if you just simply implement a global lock, you are going to get pure sequential execution. Okay? Only one query, database query or one transaction will execute at one given time, and you are going to get extremely low throughput. That's going to impact your performance of your system dramatically. So you want multiple writes to actually occur in parallel, yet you do not want inconsistencies of this sort. Okay, you had a question. Is the problem clear? Okay, now transactions are going to help us avoid this issue. Okay. Clearly, as I said, a naive approach is you just put up a lock. Okay. And that would give you the right solution, except that it's not good from a performance standpoint, it's not a good solution. Okay, so you want consistency, okay, and we'll see you want other properties as well. Okay, so whenever you talk about transactions, you want what are called ACID properties. This is again a term that is very common in databases. Okay, ACID is an acronym that stands for atomicity, consistency, isolation, and durability. Okay, that's what the A, C, I, and D mean. Atomicity means it's all or nothing. Okay? Either all of those instructions execute or none of them execute. Okay? You can't have a scenario where client executes 2 instructions and crashes. That's also going to leave your system in an inconsistent state. Okay? Because half the work is done, not the other half. So you want either everything to execute or nothing. Okay? You want transactions to guarantee you that regardless of what the client might crash, yet you don't want a situation where some of those instructions are executed. Okay, you want it to be either all or nothing. Okay, that's called atomicity. Okay, that's the first and most important property of databases is atomicity, or rather transactions. Okay, transactional databases. Okay, consistency simply says if you are in one state, consistent state, okay, once you execute a transaction, you are going to be taken to another consistent state. So the system always moves from one consistent state to another. That is what is referred to as consistency. You do not want the system to be in an inconsistent state at the end of a transaction. Okay? Isolation essentially means that also the other term for isolation is serializability. Okay? Essentially it says that regardless of how you execute those transactions, the end result should be such that they executed sequentially in some order. Okay? Because we want to define what correctness means. Okay? You want to be able to reason that this output is inconsistent, okay? But that output is consistent. Okay? In this case, it's very straightforward because there are only 2 transactions that are executing. What if there were 100? They're all executing at once. What output would you say is correct and what is not correct? Okay? The way you define that, okay, is through this notion of serializability or isolation, which simply says, okay, let us assume that they executed sequentially in some order. Okay? They are actually executing in parallel, but assume that they executed sequentially. Okay? If you could find any particular sequential execution, okay, and the output of your database is such that that sequential execution results in that output, then you are going to assume that that's correct. That's a serialized execution. Okay? That is what serializability essentially means, saying that we are going to let the transactions run in parallel. Okay, at the end, we are going to see what the output is. And if there was some sequential execution that gives us that output, we'll say that's a correct execution. Okay? If there is no sequential execution that could ever result in that output, then we'll say that that's an incorrect or inconsistent result, which is what you have here. Okay? The only two possible executions are one ran before two and two ran before one. These are the only two ways you can execute these two sequentially. In none of those two cases will you ever have B with 204. Okay? In both of those cases, B's balance is always going to be 207. So we are going to say that's an inconsistent, non-serialized execution. No serialized execution will give us that property. Okay? That's basically isolation or serializability. And the last one is called durability, which says that once the transaction finishes, okay, and there's a technical term for that, which means it commits. Okay, once a transaction is commits, then the changes are durable, which means they cannot be undone. Okay? So durability says once you have committed, then there is no going back. But while you're executing, you can actually roll back transactions. As you will see, you can undo their effects. Okay, but once you're committed, no more, you cannot undo it. Okay, so that is called durability. Okay, this is a very standard terminology in database. These are called asset properties. Any transactional system that you design these days has to give you at least asset properties. Okay, so most databases do, not all, but many. Okay. Now here is a way you will actually use a transactional system. This is not how to build one, but this is how you're going to use one. Typically, you're going to take any statements you write in your code, okay, or in a query, and put a begin transaction and an end transaction around it. Okay? And then you submit this query to your database, and then the database is going to guarantee that all of those statements are going to execute successfully or none of them are going to execute. Okay? In this case, it should be clear why you even need a transaction. So let's say in this case, you are making a plane booking that goes from New York to New Delhi. Okay? There is no direct flight, let's say, from between these 2 points. So you have to book in this case, three different segments. Okay? So your flight reservation is going to succeed if you find seats on all three flights. Okay? If you find seats on one of those two or two of those three, okay, you are not going to actually fly from the first point to the last point. You need all of them. So you are going to say reserve this segment, reserve this segment, reserve this segment. And if any of those segments are not going to succeed, then you are going to abort the transaction, which means you will undo anything that has been reserved. Okay? But if all of them succeed, then you have a successful flight booking. Okay? That's an example of how you can use transactions to make multiple operations and ensure that you get it all, or you don't care about getting any of it. Okay? You don't care if you got one of those three segments, because that's of no use to a passenger. Okay? So typically you are going to have a begin and an end transaction that encapsulates your transaction. You can also use this statement abort transaction to say, okay, this transaction is not succeeding, so just undo everything it has done so far. So it will basically go back, and if some of these had succeeded, it will undo them. Okay, that's basically what a transaction system does. Okay, read and write I'm going to come to in just a moment, but let me now switch gears, okay, having given you like a 3-slide introduction to transactions and asset properties. Okay, we'll talk about distributed transactions. That's really what we are after here. Okay, so to understand what are distributed transactions, we must distinguish them from what are called nested transactions. Okay? Nested transactions are essentially one transaction encapsulated inside another transaction. Okay, so if you have a transaction that says begin transaction and there's an end transaction, and inside it there is another begin. Here, let's say a begin transaction. This is called a nested transaction because these two transactions are nested inside this bigger transactions. It's just like a nested if. Okay, you have one if then inside another if then. Okay, so this is common even in a centralized database. Okay, this does not make the transaction distributed. Okay. Here's an example of a nested transaction, why you might even want to do something like this. Let's say you're taking a trip, you want to book an airline ticket and you want to book a hotel, okay, at the place you're going to. Okay, and you want both of those things to actually succeed. Okay, you cannot have a hotel with no plane ticket or a plane ticket with no hotel. Okay. and we'll assume that the airline database and the hotel databases are independent. So each of these reservations is its own transactions. Okay, so this could be the airline transaction and this could be the hotel transaction. Okay, but you want both of them to succeed as well, or neither of them. So you will put both of those transactions inside a bigger transaction. That is your nested transaction. Okay, that's what is shown in this picture. Okay, this does not make the system distributed. This is simply making two transactions on two centralized databases. Okay, what is a distributed transaction is shown here, where the database itself is distributed. The database does not run on one machine, it is distributed across multiple machines. Maybe it's a very large database. It does not fit on one machine. And maybe you want to scale it beyond the capacity of one machine. So your database is split across multiple machines. It looks like logically a single database. That's what is shown in that bigger disk. So it's a logically unified database, but physically it's a distributed database. If you run a transaction on such a system, you are going to get a distributed transaction, because parts of the transaction may operate on this disk or this machine, parts of the transaction will execute on some other machine. Okay? So that's different from this picture. This is nested, that's distributed. Okay? Any questions on what is a distributed transaction? Is this clear? Okay. So I will talk about how to implement transactions. Okay, so I'm going to describe two different approaches for implementing transactions. These two approaches work actually regardless of whether you're implementing a distributed transactional system or a centralized one. Same ideas work, but let's just ignore the distributed part for now and just understand how you're going to implement transactions. So remember, you want to essentially provide asset properties. Okay? And the most important thing, so we'll talk about locking in just a moment. Okay, we haven't gone and looked at how are you going to do more fine-grained locks and whatnot. What we are simply going to see is how is it possible for you to undo the effects of a transaction. So let's say you execute a transaction and either the transaction will commit, which means all of its changes that it has made to the database are made permanent, or if it aborts, you are going to have to roll back the transaction. Everything you have done so far has to be undone. Okay? So a simple way to do this is use what is called a private workspace. Okay? In a private workspace, think of it as if you got your own this transaction got its own private copy of the database. There is actually a database. Let's say you make a private copy, okay, and you hand it off to the transaction. So the transaction then goes and makes changes to the private copy, not the actual database. Okay? So all of when it's executing, it's making changes to its own copy. So now if you abort the transaction, you simply throw away the private copy. Since you not touched the actual database, the changes that are made by the transaction are not reflected in the actual database. Okay? On the other hand, if you commit the transaction, then you are going to take those changes and apply them to the actual database. Okay? And then the changes become visible to the rest of the system. Okay? That is what is shown in this picture. Okay? So this is not showing you transaction as much as disk block, but the principle is the same. So it's showing you that this database has 3 disk blocks, 0, 1 and 2. That's the index to the disk blocks. Okay? And here is actually a private workspace where you copied the index. So in reality, it should be clear that you are not going to make a real copy of the database. Okay? You can't take a 1 GB database or 10 GB database and make copies every time a transaction runs. That's not going to work. Okay? You are going to make what is called a virtual copy, which means it looks like a copy, but it's not a real copy. Okay? And the way you are going to do this is you are not going to copy the data. Okay? You are simply going to take these pointers which tell you where the data resides on disk and make a copy of the pointers. Okay? So this is basically the index you make a copy of. Okay? That's your private copy. Okay? Now if you make changes, what you are simply going to do is use what is called a copy on write mechanism. Okay? This mechanism is called COW. Okay? Copy on write. So what it does is every time you try to write to a block, okay, in a copy on write, you will not actually make changes to the block. You will make an on-demand copy and write to a new version. Okay, so here, what you see is this database has actually written to block 0. So that makes 0 prime. So the old copy is still 0, but rather than overwriting that block, which is what you would have done if you had made in-place changes, you actually make a copy of 0, on-demand copy, and you write to the new version. Okay? So in the private workspace, you are now pointing to 0 prime. In the original database is still pointing to 0. And now maybe you can write a new block, which is the only block 0, 1, 2. You write to a block called 3, which in this case is shown as 3 prime. I know that's only visible in the private copy. Now, if you had to abort the transaction, you will simply throw out this index, okay, and delete all the new blocks you've written. Okay. But if you want to make the changes permanent, you're going to take all the diff between the two index structures and simply apply the diff. Okay, in which what that means is you're going to have 0 point to the new version, as you will see, and then 3 has also appeared in the database. Okay, so this is taking the copy on write mechanism. Okay, first there are two things here. You're making a virtual copy using a very standard OS technique called copy on write. Many file systems implement copy on write. It's a very standard operating system mechanism. You're simply using this to implement a private workspace in a database. Okay, you make a virtual copy. You make all the changes to the virtual copy. Okay, and the reason it's virtual is you're making basically it's a lazy copy mechanism. You copy on demand. Okay, which is called copy on write. Whenever you try to write to a block, that's when you make a copy. Because if the blocks are not written to, why bother copying at all? Okay, you don't have to make any copies. Both the actual database and the virtual copy point to the same data blocks, and that's fine. Okay, so that's your private workspace, and then if you commit, you're going to apply the changes. If you abort, you throw it out. Yes.
If there are multiple things working at the same time, is it applied sequentially? Or
okay. Question is, if there are multiple transactions, each of them will get their private copy. Okay. When you are committing the database, you commit them one at a time. You can't have two of them trying to update the same index, so you're going to do it one at a time.
Right, but then again, so after the first one's applied, then won't the index reflection of the other copy and like now the current new state be?
Yes, that's a good question. The question is, what if there were two transactions that virtual copies, they make changes to the same block? Okay, and you write the first one, and then the second one is going to overwrite. If both of them made changes to block 0, first one will make block 0 0 prime, and the second one will make 0 double prime. You may get inconsistent. The same problem we had earlier. So even when you have private workspaces, you do not actually get around the fact that there has to be some locking, and you have to detect what are called write-write conflicts. Okay, two transactions. I'm going to talk about write-write conflicts in just a moment. This is simply showing you the picture without locks and without any conflicts. Okay, but you will have to resolve when you're trying to commit a transaction. Did some other transaction commit since this began and make some changes to the same blocks that this transaction has made change? If so, you will have to abort because you are going to get a conflict. Okay. So I haven't talked about locking and conflicts, but just wanted to show how this private workspace works. Okay, that's option 1. Okay. Option 2 is you actually do not make virtual copies, but you let the transactions make changes to the actual database. Okay. So you are going to make in-place changes. And then this also requires you to keep a mechanism that will allow you to undo the changes. Okay, because if the transaction aborts, you already made some changes, you want to be able to undo its effects. Okay? And the way you're going to undo it is you're going to keep a separate structure called a log. The log keeps track of what changes the transaction has made. So you keep a record saying since this transaction began, it made these changes. Okay? So now since you're actually recording what changes have been made, you can undo those changes by looking at the log and undoing its effects, okay? Which I'll show you in just a moment as an example. Okay? So you're going to make in-place changes. So each transaction is going to directly make changes to the database. You're going to have a write-ahead log, okay, which is going to keep track of all the writes, okay, which will be in the log. And if you're going to commit, there is no problem. All the changes are already in the database. If you're going to abort, you're going to look at the log, look at all the changes that are made by this transaction. All the transactions have an ID, so you know what changes were made by what transaction, and you're going to undo. This undo is called a rollback. You're rolling back the state of the database to where it was before the transaction started. So it looks like the transaction never even ran. Okay? So that's called rollback. Okay? And then we are going to talk about how to make it atomic. That's the locking part. But let me show you a very straightforward example of how write-ahead logs work. Okay? Here is essentially a transaction. We'll assume our database has only two values, x and y, okay, two records. Okay? let's say we initialize the transaction, or this transaction essentially increments x by 1, then y by 2, and then it basically sets x to y times 1, and x is y square. Okay? And x and y you start with 0. Okay, now as you make changes, you are going to keep a log. Okay, so this is the log. Okay, and as you execute each of these statements, the log is growing. So in the first statement, you are setting x equal to x plus 1. So if value of x was 0, it changes it to 1. So in the log, you are going to say that before the statement, the value of x was 0. After the statement, the value of x is 1. Okay? Then you execute the next statement, and it tracks that y was 0 and has changed to 2. Okay? And then you look at the last statement, and then you say x was 1, okay? And then it's changed to 4. Okay? Because it's going to set it to y square. Okay? Now, if you want to undo this transaction, you are going to do what is called log replay. Okay? You are going to simply read this log backwards and simply start undoing whatever was done. Okay? You're going to just blindly play the log backwards. So you say the transaction was to abort, restore the state of the database to what it was. Okay? At this point, remember that the state of the database is x is 4 and y is 2. That's what you actually written to the database. Okay? You want to roll it back and get back to 0, 0, which was our original state. Okay? And what you're going to do is you're going to replay backwards. So you're going to say go to x and then change it from 4 to 1. Okay? You're going to say go to y, change it from 2 to 0. You're going to say go to x and change it from 1 to 0. Okay? So once you replayed these 3 log instructions, you are back to 0, 0. Okay? That's where you were before the transaction began. And you undone the transaction. So if you want to simply abort a transaction, you'll take all the changes that were made in place, look at the log and just replay it backwards so that you are where you get back to where you were before. Okay? If you didn't keep a log, you do not know what the state of the database was, because you go and make changes and you say now undo it, you don't know what to undo it to. So you actually have to track whatever the changes are being made by the transaction. Okay? So essentially, this is this notion of a log is no more general purpose than just using it for transaction. In many other systems, including file systems, use logging these days for consistency. So you can figure out if your OS crashes while the machine was powered up, you can actually go through the log and get the file system to a consistent state using the same mechanism. Okay, databases use logs and many other systems do too. Okay? So this is just an example of a more general solution, which is use a log to keep track of changes, and then you can undo the changes by looking at what happened. Okay? So we looked at 2 mechanisms.
So yes. Separate question. What if the machine that's performing the transaction fails before executes the transaction, but after it logs the thing?
Okay, that's a good question. So question is, what if the machine executing the transaction fails? So I showed you an example where the transaction actually aborted. So you undid the law, undid its effect. Okay. Now if you have a system, let's say database system, and there are transactions that are executing in this fashion, and the machine crashes, what do you do? Okay. So in this case also you are going to do basically a rollback recovery. Okay. Because if the machine crashes in the midst of some transaction, your database by definition is in an inconsistent state, because the transactions have made some changes, they have not committed. You only basically, the asset property says that you take it from one consistent state to another after the transaction finishes. In the middle of a transaction, you are not guaranteeing that the system is in a consistent state. So if it crashes at this statement, okay, your database is not in a consistent state. It's left in some middle state where the transaction was in the middle of execution. Okay? So what you do in that case is when your system reboots, okay, you look at the log. Okay? You look at every uncommitted transaction and you roll them back automatically. Okay? So your log, what I have not shown here is the log, if this transaction commits, would also write another record here saying this transaction committed successfully. Okay? So if you simply look at the log and look at it backwards, you can see all the transactions that were in progress that have not committed, and you know all the changes they made, you simply roll them back, say they are uncommitted transactions. Okay? This is what any database will actually do. Okay, you can try this out if you want to run a database. You can actually unplug the machine might just stop. If you restart it, the database will look at the log and say what transactions were in progress that do not have a commit record in the log and simply undo them as if they aborted. That's the only way you are going to get to a consistent state. So fault tolerance or failure recovery is automatic when you do logging, because you have the ability to undo anything that was in progress. And in one case it's because the transaction aborted, the other case you undid it because the system crashed. But both of those things work. Other questions here? Okay, that is all right. So now we are going to talk about how to get. So we looked at correctness, okay, which is how can you commit a transaction, how can you abort a transaction. We looked at two techniques: private workspaces and write-ahead logging. Now we are going to come to the problem of what is called concurrency control. Okay. So as I said, a database is a shared resource. There could be many transactions that are all executing all at once. Okay. You cannot say that let each transaction take a global lock on the database and let it just run one transaction at a time. That is going to significantly slow down your performance. Okay. Think of an airline database. Okay. And think about how many people might be trying to book a ticket on an airline database at the same time. If each of them had to run sequentially, you would be waiting for hours before you actually know whether you got a ticket or not. Because each transaction is going to take some time to finish. What you want is the ability to run all of them concurrently. Okay? Yet you want correctness at the end of this. Okay? And you cannot achieve that by putting a large lock on the entire database. That is going to give you correctness, but it's not going to give you any concurrency at all. So it's going to make each of them run sequentially one at a time. Okay? So concurrency control is a set of techniques, okay, that allow transactions to run in parallel, okay, and yet it is going to give you a correct state. Okay? So if you think about this, you want, in the very first example that I showed you, you want these two clients to run concurrently, yet you want the state of the transaction to look like they ran sequentially. Okay? From a correctness standpoint, it should look like you are running sequentially. From a performance standpoint, you want to let as many of them run in parallel at once. Okay? So it's not a trivial problem to achieve this, but I'm going to show you some techniques that are used to implement concurrency control. First, I'm going to show you some system level approaches. Then we are going to look at some actual techniques. Okay? Typically, a database system which is going to implement any concurrency control is going to look like this. And there's going to be a transaction manager that tracks which transactions are in progress. Okay? There is going to be a scheduler that's going to schedule all the instructions, okay, that are within a transaction. Okay? And then that scheduler is also going to take locks, okay? Except that these are more fine-grained locks. Okay? Rather than locking the entire database, assume that there's a lock for each row of the database. Okay? You want to say, I want to only take a lock on all the records for this flight 100. Okay, but the airline might have hundreds or thousands of flights. You don't take a lock on anything. You only take a lock on the part of the database you care about. Okay? So you have more fine-grained locking in databases. Okay? So the scheduler is going to take locks only portions of the database. Okay? And yet you want to ensure that problems like write-write conflicts, all of them go away. Okay? And that is what concurrency control allows you. Okay, just because you locked a small part of the database doesn't mean you're not going to get a write-write conflict. You might take a lock, release it, some other database transactions may have read the data before and make some changes and you're going to get into trouble. Okay, so you still want serializability, which means you want the results to look like each of them ran one at a time. Okay? Is that clear what the goal is? I haven't shown how to solve the problem. I'm simply showing you a system that actually implements a layered approach, okay, where you have a transaction manager, you have a scheduler. The data manager is simply a file system. It's simply implementing reads and writes, okay, to the underlying data. Okay. Here's a picture of what a distributed concurrency control looks like. Because we are talking about distributed transactions, okay, these machines, there may be more than one machine. Okay. So you have a transaction manager, but then the locks are taken on the parts of the database that reside on individual machines. Okay, so there's a scheduler for each machine, okay, that talks to the transaction manager. Okay, so the locking is done on a per machine basis. a data manager is reading or writing the underlying data also on a per machine basis. Okay? So this notion of how centralized databases implement concurrency control, okay, is going to generalize to a distributed database as well. Of course, I haven't shown you how to take logs and all of it. That's the concurrency control algorithm that we have not looked at, but this is the system that might implement such techniques. Okay. Okay. So now I'm going to talk about serializability and then look at locks, read, write locks, and write all of that kind of stuff. Okay. So here are three transactions. Okay. This is the first one, this is the second one, this is the third one. They're all making changes to the same record of the database, which is X. Okay, let's say the database has only one value for simplicity. Okay, that's the variable X, and they're all making changes. Okay. Now, since we want concurrency, okay, we are going to let them all run in parallel. Okay. And then we are going to reason about, at the end, if you look at the value of X, we are going to reason about, is this a legal value or an illegal value from a serializability standpoint. Okay. The idea is if you find any sequential execution that gives you that value, we'll accept it. If you cannot find any sequential execution that gives us that value, we'll reject it as inconsistent. Okay. Is that clear what serializability means? Okay, is that clear or not? So let's look at an example and maybe we'll come back to that question. So here is, so we'll see arbitrary, because they're running in parallel, we don't control what order they run. Okay, they are just going to get interleaved in some fashion. Okay, here is one interleaving, okay, of those 6 statements. Here's another interleaving, this is the third interleaving. Okay, so here you have x equal to 0, then incremented by 1, then you again set x equal to 0, incremented by 2, set x equal to 0, incremented by 3. Okay, and we said that is acceptable. That leaves x as x equal to 3. Are you convinced that's a valid interleaving? Okay, why is it a valid interleaving? Okay, so to reason about whether that is a correct end result or not, you have to find some order in which those 3 transactions ran sequentially. And if that ordering gives you the same output, then you say that's legal. Okay, so then the question is, for this interleaving, what is the sequential ordering in which these 3 transactions ran that gives us that output?
ABC.
ABC. Okay, there's actually no interleaving here. If you read these statements, these 2 statements are executing first, and those 2 next, and those 3 at the end. So they are actually executing in sequence. Okay? And that's valid because you say if there was a sequential execution, if you ran this one first, and then this one's next, and this one third, you would end up with x equal to 3 because each of them is resetting x and then simply adding some value to x. Okay? So x equals to 3 is a valid output for these 3 transactions. Okay? For that sequential execution, not all of them may result in that. Okay? Here is another one. Okay? So here you have x equal to 0, x equal to 0, then you increment x by 1, then by 2, you reset x equal to 0, and then you set x equal to x plus 3. Okay? So now if you see there, it says it's legal. Okay, the question is, are you convinced it's legal? And that also leaves x equal to 3. But what you'll see, what's happened in the middle is you actually went, basically you have this statement and that statement execute one after another, which if you had actual sequential execution would never have happened. Okay? But yet, since the end result of these three transactions is x equal to 3, okay, we don't actually care what happened in the middle. Okay? Before you started, the database was in a consistent state. At the end of this, okay, we end up with x equal to 3. That's a consistent state because a serial sequential execution of these 3 would also leave us with x equal to 3. So we will accept it. Okay, so that's also from a serializability standpoint, you will say that's an acceptable outcome. Okay, So that's basically a valid end result. Okay. Here is schedule 3 that is going to leave us with x equal to 5. Okay, because if you look at what has happened, set x equal to, you do this, you set reset x to 0, and you increment it by 2 and 3. So that gives us x equal to 5. Okay, and we said that is illegal. Okay, you have something to say.
So since A, B, and C are concurrent these things, why are we assuming that the sequential will be A, B, and then C?
It does not matter which order you pick. You have to pick some order. If the end result was x equal to 1, we would have accepted. We would have said one of these two ran before this one. X equal to 1 is valid. X equal to 2 is also valid.
But wouldn't that be inconsistent, because now you're reasoning that your database would have 3 possible values when at the end it's supposed to have 1 consistent value?
In general, yes. But if you look at this, because you don't control the ordering, we will take any ordering. Okay? It doesn't mean that all orderings will actually end up with the same output. Okay, in this case, because we have a very weird example where the x is getting reset. Okay? If you added reset x, then you would basically, if you started with x equal to 0 and you executed them, you would end up with x equal to 6 no matter what the ordering was. But this is a weird transaction. Okay? But we are just simply following rules. We are saying, doesn't matter, pick A, B, C, B, C, A, C, A, B, doesn't matter. Pick some ordering, if that is the output you get, we'll take it. Okay? In general, the ordering should end up with the same end result, I agree, but this one does not. That is why it's actually a little bit of an odd example, but nevertheless, the principle of serializability applies. Okay. Now the question is, x equal to 5 is an illegal state for a database, for this database. Okay. The question is why? So this last interleaving will not accept as a legal interleaving. Okay, so what is this telling us? Why is that illegal? Yes.
No matter what order you choose for serializability, it's never going to end up this way.
Okay. So all you have to do is say, if I ask you is x equal to 5 valid, you just have to mechanically enumerate all possible ways of doing the serial execution. You say, let me do A, B, C. What do I end up with x equal to? Let me do A, C, B. What do I end up with x equal to? You try all possible sequential ordering. Okay? If none of them give you x equal to 5, then you say there is no possible way these could have executed in some sequential order and ended up with x equal to 5. That's just not going to happen for any ordering at all. So this can never happen if they were executing sequentially. So it's illegal from a serializability standpoint. Yes, question.
What if we end up with something that's weirdly interleaved, but still ends up with a legitimate output? Like we do it instruction C completely, or transaction C completely, then we do the 2 sets equal to 0, and then the 2 plus 1.
That's this ordering is actually going to see if in the middle you are going to do these 2 statements first, then you're going to do this and this.
Yep.
Okay, and then you reset it and go back. So in the middle you have something that you would not actually have gotten. If only these 2 had executed, you have ended up with x equal to 3. This transaction hasn't even begun. Okay? If you have these 2 executing sequentially, you will never actually get x equal to 3. You will get either x equal to 1 or 2. But if you look here, because of this interleaving, you ended up with an inconsistent intermediate state. But we ignored that. We said at the end, you're still consistent. That's all we care about.
So if we had the middle line, schedule 2, but we stuck C at the very beginning, then our output would have been the legitimate output for transaction C.
Yes, we would have accepted it even though it looks pretty fishy, right? Because x equal to 3, this is a very odd example. You shouldn't actually have cases like this, but in this case, we will actually take it. Because you might assume, because you don't know exactly what happened, you might assume this is the one that ran the last, even though these 2 actually are getting you to x equal to 3. Okay? Yes?
So does this mean that you shouldn't do reads in the middle of a transaction? To say like in schedule 2, if you had like, it works out in this case I suppose, but in the middle when it was like x plus 1 and x plus 2, if you had like another case where it was x plus 2 and x plus 2, you then have the output of 4.
This is where we started off with. You did a read in the middle of a transaction, okay? You read B, some other transaction went, read B, overwrote it. Now you are using an old value of B and trying to reason on that and ended up with an inconsistent result. So that is exactly where write-write conflicts occur. If you try to read a value, okay, and while you are working on it, some other transaction reads it and modifies it, then you end up with an old result. Okay?
Sure.
That is going to give you, this gives you exactly the problem you are mentioning. So yes, when you have reads in the middle of a transaction, bad things can happen if other transactions also read the same value and change it for you. Okay? Which basically gives us these two things that I was going to come to. So what this is showing us is, the reason this odd example is actually worth looking at is because there are all sorts of odd interleavings that still end up with a valid result. There are of course some interleavings that give us no valid result at all. Okay? So what you really want is the way to schedule conflicting instructions, okay, such that there are no conflicts. And we are going to distinguish, based on whatever we have just discussed, with two types of conflicts. A read-write conflict is one where you read the value of some variable in the database, okay, and then you write to it, but something else has modified it in between. So you end up with an incorrect result. Okay, this is exactly what I just showed you. Okay? And write-write conflict is you just go and clobber some other transactions writes, and then again you have a bad result. Okay, that's going to, so if two transactions try to write to the same value, okay, that's a write-write conflict. If you read something and write to it subsequently, but something else modifies it, that's also a read-write conflict. So you want to avoid both of these types of conflicts. And the way you are going to do this is to implement some form of locking. Okay? Until now, there were no locks. We are just saying you would let them run wild and interleave themselves in some way. That's not how real systems are going to work. They are going to take locks. They won't take global database locks. Okay? That's going to give you sequential execution, but no concurrency at all. If you hold a lock, nothing else can run. Everything else is blocked. So you want more fine-grained locking, yet you want to avoid these kinds of problems. Okay? And then the way we are going to actually do this, we are going to describe two approaches. Okay? One is called an optimistic concurrency control, and then we look at pessimistic concurrency control. Okay? In optimistic concurrency control mechanism, okay, you are going to get the maximum possible concurrency. Okay? There will be no concurrency control technique that gives you any higher throughput. This gives you the best performance. Okay? And you will see why in just a second. Okay? But there will be problems because you are trying to trade performance for correctness. Okay? So what optimistic concurrency control technique says is, let's be optimistic that there may be multiple transactions in progress, but because our database is large, they may be working on independent parts of the database. Okay? And hence they may never conflict with one another. Okay? So if that is the case, why implement locks at all? Let them run without any locks. Let's be optimistic. Okay? Let them make whatever changes they want. Let's not have any locks. But while they are about to commit, we are going to do some checks, saying, since you started, has anything else come and run and made change? If so, you are going to abort. If there is no other transaction that's touched these records that you read from, then there is no conflict by definition. The conflict only occurs if two databases work on the same data at the same time. If the transactions are working on separate parts of the database, then there is no problem. Okay? So that's an optimistic concurrency control technique. Okay? A simple example is in your airline database. If two passengers are making reservations and looking at two independent flights, those two transactions should not conflict by definition. Okay? Because you are looking, let's say, to go to California, somebody else is looking for a flight to go to Europe. There are different flights. Okay, so they could run in parallel without any conflicts whatsoever. Okay, so you could say let them run without locks. When they're about to commit, you're going to see did they touch the same data. If they did not, then there is no conflict. Yes, you will let them come. If they did, then you will abort. Okay? So the optimistic concurrency control technique is the simplest one. It says let's not have locks. We'll live in a lock-free world. Okay, so essentially you'll get maximum parallelism because there's no locks. There will never be any blocking for a lock. Okay, all the checks are done after the fact, saying did anything bad happen? Did some other transaction touch any data you touched? If so, you are going to abort the transaction. Okay? So the insight here is conflicts are going to be rare, so it works well for most of the time. Okay? Not all the time, but most of the time. Okay? So there are many advantages. Okay? By definition, optimistic concurrency control is going to be deadlock free. Is it clear why?
There is no lock use.
So there are no locks, so how can there be a deadlock if there are no locks? Right? So that's why I said by definition it's going to be deadlock. So we don't use locks, so no deadlocks. Okay? maximum parallelism. So all of those problems are gone. Okay? The disadvantages are, because you're taking an optimistic view, if there is another transaction that touches the same data you are reading or writing, okay, you are going to have to abort and rerun the transaction. Even whether there are conflicts or not, for safety, you're always going to abort and restart. Okay? And then the second disadvantage is the probability of conflicts will rise as the load on the system increases. As there are more and more concurrent transactions, the probability that any two of them by random chance conflict with one another keeps going up. Okay, so at high loads, okay, you will basically have high abort rate, okay, which means that your throughput is going to fall. Okay, what is called good put will fall. There will be lots of transactions executing in parallel. Okay, but good put, which is the number of transactions that are actually finishing, is going to drop because a lot of them run. If you find that something else has conflicted, they terminate, they restart. Okay, they run again, then they find that something else is conflicted with them, they restart. So there will be a lot of transactions doing a lot of wasted work and not able to finish. Okay, because there will always be high probability of a conflict. Okay? So the disadvantage is your good put is actually going to drop at high loads. Okay? And because of that one last reason, although optimistic concurrency control by and large works well, okay, no commercial database actually uses optimistic concurrency control. Okay? Because it does not make for a good selling point. If you tell your customers it works well, but when the load goes up, it's not going to go. That's the time when you actually want more transactions to finish, because the load is high, and if more transactions start failing when the load is high, your customers or the applications that access the database will not actually get their work done. Okay? So, not used as well. There will be lots of papers. If you actually look at any database conferences from a few years ago, you will see lots and lots of papers on optimistic concurrency control. Okay? So it seems like a good idea, but it hasn't been adopted in practice because of the last problem. So you cannot actually make it work well when the load is high. It works very poorly when the load is high. Okay? So that's optimistic concurrency control. Now we look at actually the other approach, which is pessimistic concurrency control. So in this case, you basically take a more conservative approach. You say conflicts are always possible. Okay? So we'll use locks to avoid them. Okay? So we'll basically try to get rid of read-write and write-write conflicts by taking locks. And the standard approach in databases, which also works for our distributed transaction, is called two-phase locks. Okay? It's called 2PM. Okay, in databases, two-phase locking. Okay? So it's a very widely used concurrency control technique. Okay? It's best explained with a picture. Okay, so essentially every transaction is going to have what is called a growing phase, where it keeps acquiring new locks, and a shrinking phase where it starts releasing locks. Okay? And so here's a picture which is shown with the graph with time on the x-axis and the number of locks that is held by the transaction on the y-axis. And as is shown in the growing phase, as you touch new data in your database, you are going to first grab a lock. Every time you touch a record, you are going to first grab a lock on that record. Okay? So in the growing phase, you keep acquiring locks. Okay? And then once you are actually done accessing all new data, then you are going to start releasing locks. Okay? So this is your shrinking phase where you released one lock because you're done with, let's say, some record, and you released another lock and so on. Okay? There is a variant of this approach. Before I explain the intuition, there's a variant of this approach called strict two-phase locking, where the shrinking phase is actually replaced by the transaction end, where you release all lock at once. Okay, so the only thing that's going to happen in the growing phase is, as you touch, anytime you need to read or write another record in your database, you're going to grab a lock. So you keep on acquiring locks. Okay? You hold them all until the end. So your shrinking phase basically just release all of them all at once, which is a much simpler approach than trying to look at when should I release this lock and the other lock and so on. Okay, so that's basically how the two-phase locking works. So let's talk a little bit about intuition about what this is going to give us. Okay? So essentially what happens is you check an operation on data item X, and if that conflicts with some other existing locks, you are going to wait because you are grabbing locks. Okay? If you try to grab a lock on X, if some other transaction holds the lock, you're simply going to wait. Once you hold a lock, you're guaranteed that until you release the lock, no one else can come and touch that data item. Okay, is that clear? So let's say you have a begin transaction, you have an end transaction. Okay, so we read X, Y, write X, update Y, something like this. Okay, so the first time you touch a data item, you are going to basically, this is what your code is going to look like. When you give it to the transaction manager, when the first time it sees X, it's going to tell the scheduler, go get a lock on X. Okay. And it sees this, you will say, go get a lock on Y. Okay. And then you basically go X, write Y, you already hold a lock. And when you have an end transaction, you're going to release all this. So these locks are going to get acquired dynamically as you touch every new data item. Okay. And the issue is, once you get a lock, you are guaranteed that there will be no transaction in the system that is going to modify or read X after this point. Because you first have to grab a lock before you get it. So once you have actually a lock, then no other transaction can conflict with you. Okay, is that clear? What I just said? So, and if some other transaction already holds a lock on X, okay, if you just take that strict two-phase locking protocol rather than this one, if once you hold a lock on X, while you're doing this, if some other transaction is holding a lock on X, okay, it will basically release the lock when the transaction ends. So by this definition, you cannot have a conflict anymore because that transaction is already finished. Okay? So you will basically block if some other transaction is working on any data that you are worried about or you're going to work on. And once you grab a lock, you'll block all other transactions that try to access any data that you are accessing. As a result, because of two-phase locking, you are going to avoid either read-write conflicts or write-write conflicts. Okay? And yet you will get concurrency because the locks are on a per data item, not for the entire database. Okay? So other transactions that access all these other records can execute in parallel with this because you're going to work on independent parts of the database. They don't work on the same data at the same time. Okay? So you are going to get concurrency. Okay? Yet, because you are grabbing locks, there will be no conflict. Okay? Once you actually commit, you will be sure that there will be no conflicts of horizon in the middle. Okay? Whatever I just said for this is also true for two-phase locking, but you have to have more of a proof to believe that if I release a lock on X here, some other this transaction hasn't finished. So if some other transaction goes and grabs X, it's still not going to result in a conflict. That requires more of a proof. But let's ignore that proof. You can just assume, at least for strict two-phase locking, you should be clear that there are no conflicts because you hold locks all the way to the end. Okay, the same idea is going to apply to both our centralized database as well as distributed database. Okay, because you're just going to go grab locks from multiple machines. That's the only difference between the two. Okay, because whether it's strict or not strict, if you look at this picture, okay, the transaction manager is basically going to run this. It may be that X is on machine A, Y is on machine B. It doesn't matter. You simply have to get the locks from the right machines and read or write data. Okay? The same principle is going to apply, regardless of whether this is centralized or distributed. Okay, yes, question.
Are we going to assume that on failure they just drop all the logs?
Okay, that's a good question. So, question is what happens on a failure? Okay, it depends on what is failing. Okay, the application that is actually executing this may fail. Okay, that's okay because the transaction is actually executed by the database, not the application. If the database can release the locks. Okay, if the database itself fails, then you have to restart the database. Okay, it will basically release all the locks and every uncommitted transaction will be rolled back. Okay, that's what we are assuming in this case. Okay, but that's a good question because failures are actually an issue. Okay, so now the last thing is, first of all, now it should be clear that this is actually going to avoid conflicts. Right? What may not be clear is that even though we have avoided conflicts, deadlocks are still possible in this case. Okay, so let's try to construct an example with a deadlock. Anyone written code that gives you a deadlock? What's a guaranteed way to get a deadlock? Not a guaranteed, but easy way to get a deadlock. Not ever guaranteed. When we construct an example with for two-phase locking, that will give us a deadlock. Okay, you need two transactions for sure.
So it's another transaction want to read Y first and then read X. So the first transaction will get locked for X and wait for, and second transaction get locked for Y. So they will have the first one waiting for the second one to release the lock, and the second one waiting for the first one to releasing the lock for X.
Okay. So the example that was just mentioned is exactly this example here. Okay. Two transactions. This one starts working on X first and then Y. That starts working on Y and then X. Okay. They are both running concurrently. You may get a scenario where this statement executes and now you get a lock on X. Okay. And then you will switch to this transaction which will execute and get a lock on Y. Okay. Now when you come back to the first transaction and try to get a lock on Y, you are going to block because this transaction holds that. And when you come here and try to get a lock on X, you are going to block because this transaction holds it. So now you have a circular wait where each transaction is waiting for some other transaction to release the lock, and you have a cycle. So that's on a deadlock in this case. Okay. So we did two-phase locking, okay, exactly what we were trying to do, but now we ended up with a deadlock. Okay. So two-phase locking by itself will not guarantee that there will not be any deadlocks. Okay. It will guarantee that there will not be any conflicts, because we'll avoid read-write and write-write conflicts by getting locks. But deadlocks are possible unless the lock manager actually does something smarter. Okay, so you have to actually use other techniques to ensure that you will not have deadlocks for two phases. Okay, any questions here? Okay, so we looked at locks. 2PL, we looked at strict 2PL, and now we are going to look at yet another technique, which is going to bring us back to our Lamport's clocks. If you remember, we used Lamport's logical clock for a number of different reasons. We are going to also use it to implement a timestamp based concurrency control technique. Okay? So here all we are going to do is the following. Okay, we are going to use logical timestamps. Okay, we are going to use Lamport's clock. We are going to assign a timestamp to each transaction when it starts up. Okay, and then we are going to look at whenever a transaction tries to access a data item, we are going to look at what is the most recent transaction that has actually accessed this data item. Okay? If a newer transaction has started actually modified or read this data item, that's for us a conflict. Because you are trying to read something, the transaction that started after you has already gone and modified it, so that might result in a conflict. Okay, so you are going to essentially abort the transaction because you can't have a new transaction that's modified data being impacting an older transaction. Okay? And we are simply going to use timestamps to enforce this property, okay? Which is essentially what is shown here. I'm going to run through that technique quickly. Okay? So every transaction Ti is given a timestamp. That's the time at which it started. That's the start time for that transaction. Every transaction in the system has a start time, which we will call Ti. Okay? So if transaction I wants to do an operation that conflicts with transaction J, okay? Basically what that means is you try to read a data item that's already been read by another transaction J, then you are going to abort if J is newer than you. That means the timestamp of J is actually greater than your time. That's the principle. You cannot have, once you start, you cannot have newer transactions go and try to modify or read or write any data you are interested in, because that's going to cause some problems. So you want to basically have data be changed in a sequentially increasing order. That is going to give us sequential serializability. And that's what this is basically a simple way to enforce serializability. Okay? And the way we are going to do this, so basically if that happens, then you are going to abort the transaction and restart it with a newer and larger timestamp. which point it might succeed if no other transaction accesses that data. Okay. And then to avoid read-write conflict and write-write conflicts, we are going to actually, for every data item, keep 2 timestamps. With the transaction itself as a timestamp, every record in your database will have 2 timestamps, a read timestamp and a write timestamp. Think of it as the last time the data was read and the last time the data was written. Okay, so you basically have the most recent read time and the most recent write time for every data item. Okay, that's the timestamps. Okay, so here's the simple technique that's going to prevent it. So if you want to read a transaction I wants to read X, you're going to look at the timestamp of transaction X, and then you're going to look at the write timestamp. Okay, if the write timestamp is newer, okay, that means the newer transaction is already written to X, and you are trying to read it. Okay, that's going to cause you to abort that transaction. That's a read-write conflict. So you just found a read-write conflict where you are an older transaction that's trying to read something, a newer transaction has gone and modified the data item already. So you flag a read-write conflict and you abort. Otherwise, you're going to read X and you're going to update the read timestamp to your timestamp. Okay. And the write is going to do the same thing. If you want to read or write X, you're going to compare the transaction timestamp with the most recent read and the most recent write. So in this case, if any newer transaction either read or written to that data item, you are going to abort the transaction because that might lead to either a read-write conflict or a write-write conflict. So you abort it, otherwise you perform the write and you update the write timestamp. Okay. So this is simply using timestamp-based concurrency control. It requires you to implement logical clocks. It's not using locking, but it requires you to implement logical clocks on top of the system. If you use Lampert's clocks, you can actually use this mechanism to enforce an event ordering. Essentially, you are using event ordering here. You are comparing timestamps, either using vector clock or logical clocks to reason about in what order the transaction started. Okay? By comparing these timestamps, you can figure out in what order they started. And then any newer transaction that's trying to read or write, you basically say is a conflict. And you abort. Yes?
I'm a bit confused as to why the older transaction would have to abort. For example, if you have a very complex one that needs to access a lot of different variables, wouldn't that always lead to having to abort that and start over and over again?
Yes. So in that case, so if you have a long transaction, it is accessing a lot of data, you would basically have to abort it because some newer transactions are coming and changing. Now you are asking, also asked a separate question, why is the older transaction aborting? Why is the newer transaction not aborting? So think about what would have happened if this was using pessimistic concurrency control. If you had taken a lock, what do you think would have happened? If this is an older transaction, it should have gone and grabbed all the locks it wanted. Okay. So then, if this new transaction shouldn't even have started in that case, a newer transaction would have been blocked. Okay. So now, because we don't have a lock, a new transaction has gone and modified that data, which would never have happened in a pessimistic case. This would have run and then that would have run because it started later by definition. It should have asked for the lock later. So we are trying to emulate what would have happened if you had done pessimistic concurrency. The pessimistic concurrency control, the transaction that starts first, should typically get the lock first and block later transactions. Okay? If some later transaction went and wrote it, that means that's a bad thing for us because it shouldn't have happened. Okay? So we try to just abort and say this shouldn't even be happening. Okay? That's the intuition. Any other questions here? Okay, so we are going to stop here today. Okay, this should give you some sense of transaction. If you are not clear on some things, take a look at the book after the exam. This is not on the test. You can come and ask me. I'm happy to explain more. It does require you to understand locking and so on. Okay, so again, for those of you who came in late, we do have a test tomorrow. It's going to be at 7 in this room. Okay, and if you're not a CS student, you will know, you should know that the doors get locked at 6:30. Okay, but we'll have someone standing there to let you in, but try to enter from this door. Don't try to go and look for some other doors and enter because we won't have people at all entries, okay, only at this one. Okay, if you have a CS student, you will have a swipe card or just come inside the building before 6:30 and you should be fine. So, okay, one of those. But either way, just make sure that you are here by 7 because we are going to start the exam at 7. Okay? All right. Thanks.